Greetings and welcome to EP1, the first in a series of energy equation discussions. My name is David Golding from KartaSoft, and I'll be moderating today's conversation. Today's topic is how a robust physics-informed model can unlock enterprise values from imperfect data. Bit of background, KartaSoft was established in 2021 by James Walsford. The company was founded to solve one of the most pressing challenges facing critical infrastructure today: how to make fast, informed decisions in the face of uncertainty. Our mission is to deliver physics-informed AI that doesn't just learn from data, it understands the real-world systems behind it. In this, our first roundtable, we are challenging a common belief that gold standard data is essential for predictive success. However, in reality, most industrial data is messy, incomplete, and inconsistent. Yet organizations are making real progress by embracing this messiness, using physics-informed AI to extract value, build trust, and drive outcomes. Today, we will explore how KartaSoft's physics-informed AI is helping Fortune 500 companies in the oil and gas sector turn data challenges into competitive advantages. Our expert speakers today are Dr. Ian Oppermann and David Cleminson. Good morning, Ian, and good morning, David. Introducing Ian Oppermann, someone you probably know, everybody will know. Ian is a visionary technologist, strategist, and advocate for ethical innovation. Ian brings decades of experience at the intersection of data science, public policy, and digital transformation. With careers spanning leadership roles in governments, academia, and industry, including his tenure as New South Wales Chief Data Scientist, Ian has consistently championed the responsible use of data to solve complex societal challenges. His work has influenced national frameworks for data sharing, privacy, and digital inclusion. Ian sits on the KartaSoft Advisory Board, where he guides our strategic direction in areas such as digital transformation, ethical AI and data governance, and decarbonisation via data. I'd now like to introduce David Cleminson. David is leading KartaSoft technology and strategy as Chief Technology Officer and Global Head of Critical Infrastructure and Defence. With over 2 decades of executive experience, David has built a reputation as a trusted advisor to governments, defence agencies, and enterprise leaders. His career spans senior roles in both corporate and consulting environments, where he has led large-scale transformations, aligned IT and OT strategies, and delivered mission-critical outcomes. At KartaSoft, David is heading the operationalisation of our physics-informed AI platforms, ensuring it meets the rigorous demands of safety-critical systems, resilience, and predictive intelligence to infrastructure organisations worldwide. Welcome, David and Ian. Now, we'll move into a series of questions, and I'll ask these questions and then ask our advisors to have some comments. The first question I'd like to raise, the first topic is one that we hear all the time. Let's address the myth of gold standards data and possibly reframe our expectations around data quality. So, David Cleminson, I'll open to you. Firstly, do we really need gold standard data to predict failures? I understand this has been a common belief for many, many years.
I think what it boils down to is gold standard data is a luxury, right? What's essential is robust and resilient models. If you look at utilities, oil and gas, and various large asset industries, the data collected is noisy. There's a lot of anomalies in the data, and when it comes to using this data to generate predictions, your models need to be able to deal with this type of data. Ian, any comments?
Yeah, it's partly a truism that you need gold standard data if you do things in a sort of traditional way. There's a lot of algorithms that work really, really well if you've got very high quality data. And those of us who were once upon a time researchers sat in labs and got better and better performance from our algorithms, squeezed the last drops out because we used perfect generated data. The reality is those algorithms really start to degrade rapidly when you introduce errors or noise or fuzz. So the reality is once you move out of the lab, you don't have gold standard data. The challenge then is to develop algorithms which have knowledge around of the world around them, which are informed by things other than just following the trail of data in order to do something useful and pragmatic. That's the real world practical scenario. You don't have, as David was saying, you don't have gold standard data. If you've developed your algorithms based on it, you're on a hiding to nothing. So using other knowledge of the world, other knowledge of the systems is really what's important.
Okay, so what you're really saying there is that gold standard data is, as we said, a common belief that it has to be gold standard, but really a lot of industries actually have messy ones and potentially weak signals, if you like, inside that messy data. So, David, back to you. How does physics-informed AI detect these weak signals in messy data?
So when it comes to physics-informed AI, it's actually we're using physics-informed machine learning. So it's basically physics models that are assisting that are integrated and assisting the machine learning process. So once the with that machine learning process, the system is able to identify what is noise, what is an anomaly, and what is an anomaly. And through that process, it's in essence creating models and taking into consideration the noise.
Let the pendulum swing all the way across to the other side. Once upon a
Yes.
time, a lot of people used to take purely physics-informed models out and try to apply them in the real world. And typically, models based strictly on equations fall apart when you face the complexity of the real world. The most practical solutions, the ones that deliver the most values, are the ones which use I use the expression knowledge of the world around us. So that really understanding of physics augmented by data, and the two together really are the most powerful. The world is a really complex place. All systems are really complex. So simplistic physics models aren't really up to it. And again, if you're assuming that you've got perfect data, you're on a hiding to nothing. So the ability to combine the two in a meaningful way is what really delivers the most value.
But to some extent, you're really looking at how do you actually build some sort of trust in that data as well. And I might refer in to yourself and look at the word trust and how we can build trust without having perfect data and what the role of transparency and explainability might be inside these data lakes. If any comments on that area that you'd like to share?
You're pulling on a very, very big topic. We're pulling on a thread which unravels a very, very big topic. So the many organizations feel they both simultaneously don't have enough data and have too much. It's a very strange paradox for people to find themselves in. And partly it's about understanding which data is fit for the purpose you want to use it for. And that in itself is an interesting challenge, partly because there's strength in weak signals, and sometimes those weak signals are reflected in data sets. So identifying the golden thread data sets and the ones which are second order and third order is part of the art and craft of doing data analytics, doing data science. But in each case, every data set is incomplete, every data set has bias in it, every data set doesn't have full coverage, and every data set is far from perfect. The ability to combine those takes quite a lot of care. And then the question is, once you've combined those things, is it really, is what you're looking at really fit for the purpose you're looking to use it for? And once you create your insights, your alerts, your alarms, your decisions or actions, how do you ensure that you have appropriate restrictions or recommendations or guidance for use about how to use them? Now, that all sounds possibly straightforward, but the practical reality is that if you're building a predictor or a classifier or something which detects anomalies, you want those weak signals in and to give you the inside edge as to identifying that event. But you also want to make sure you're not creating false positives. You're not creating essentially a noisy output. So it takes real craft and care to look at appropriate use, and then to build confidence in the reliability of whatever it is that the outcome you look at. Predictor classifiers are probably most relevant to the scenarios we're looking at the moment. And that takes real care. Once you've found frameworks for saying, this is appropriate to use for this quality of data, and I need a real expert to look at this, whereas I've used better quality data or better models or more knowledge about the outside world, which can rule out anomalies, then that can be used by a broader set of people, and then you create models which can be used by a much broader set of people. The degree of control and expertise that you need to have in place depends very much on the interaction of those different sorts of data, and of course how much real world knowledge you're able to bake in, so how much physics informed you're able to bake in. So the answer is a complicated one, unfortunately, but building confidence, building an understanding of the reliability of your predictor classifier really comes with the art and care and craft, understanding your data and how much real world restriction or real world filling in of the gaps you can put in place through that physics informed component.
Okay, so you talk about confidence and trust. But then you've got to have these models. How do you then take these models if you have that confidence and trust, but how do you integrate those into operations on safety addressing, like continuous learning and integration? So for Dave Cleminson, for example, as assets age and environments shift, how do models stay accurate and accurate, and they have to be useful? How can we get to meaningful actions from all this aging data that we've been collecting?
I suppose it's about continuous learning, right? So when you're building your models, it's not a set and forget. We build a model and we keep it, and that's it. What happens is as you use your data and you identify all of these, and you get your outcomes, you also produce reports on the performance of your model, so that you can actually monitor how your model progresses. Over time, the assets you're monitoring will degenerate, right? They'll break down. They'll go out of service. Whatever failure modes occur. But as part of that, your model needs to keep learning. It's more of a circular system as opposed to set and forget. The key thing there is continually analyzing how your model's performing, how it learns, and the results. And it's not just about creating the report at the end for the outcome. It's also about maintaining that model and maintaining the performance of that model during the process.
So what would you see as the real world data advantages? What do they look like in practice?
So from a KartaSoft perspective, we're providing asset intelligence, right? So we'll take assets, we'll take the historical data, we'll take the existing data, and then we'll use that for our machine learning process. And as more data becomes available, so we'll use that for testing, and then pull that to update our model to make sure it keeps learning and keeps relevant. Now, the insights that come out of that, right, will through our process with physics-informed AI, the physics-informed machine learning, we're able to predict asset failures 3 to 6 months ahead of any leading indicators. So take an example. I have a gas pipeline that's 147,000 miles of gas pipeline, right? And I want to know where those failures are. This is where KartaSoft comes in, because we can actually predict, we can actually enable these organizations to apply maintenance, right? And through that application of the maintenance, where they apply it, will save them a hell of a lot of money. Instead of going and trying to do things blind and looking at various pipelines and potentially or other assets,
So what makes the KartaSoft model more resilient than, say, traditional machine learning or other models? Ian, I might pass that one to you initially.
So the secret is physics-informed AI, and there are a couple of parts to that. A model of the real world is almost always overly simplified in order to become tractable. And when you embrace the complexity of the real world, the model becomes really, really complicated. I mean, take anything, any system, any complex environment. The physics is typically not up to describing all the nuance and detail. Data in itself is, as we've discussed quite a lot already, typically messy and noisy, imperfect, not full coverage, and contains bias. But the two together, carefully combined, can actually give you a really powerful combination. The physics essentially says this is the limit of possibility. The data says this is what's actually going on, but with some noise and fuzz in it. And if one can inform the other, physics-informed AI, then you can converge and take the best of those two worlds and actually produce something which is really quite powerful. David previously was talking about being able to predict 3 to 6 months in advance for infrastructure failures. That's extraordinarily powerful. To be able to say, I will reroute my maintenance, I will reroute my where I'm investing in order to prevent a bad event, prevent an anomaly by predicting that anomaly. It might be a failure, it might be some sort of breakage. That's extraordinarily powerful for anyone who's got a large complex system who is otherwise doing their very best to monitor and sense, and in some cases use good old-fashioned common sense to try and schedule maintenance. And when you've got 100 kilometers or 1,000 kilometers of pipeline, common sense doesn't really help you a lot. It might get you a little way there, but the system is far too complex for any human being or any group of human beings to say, this is how we should coordinate. If it's just based on sensors, there are limits to how many sensors you can put in the network. So apart from the capital cost of putting sensors in place, you've still got this issue of monitoring imperfect, incomplete data sets and then doing your best. The combination of the two, physics-informed AI, when the physics says this is as much of this complex system that I can model with equations and literally the laws of physics, which is why we're talking about physics-informed, augmented by a really good understanding or a really good sense of what's going on through a variety of different data sets. That's pretty powerful. And the differentiator ultimately is the ability to merge these two complex worlds together in a way which gives you something that delivers that real world outcome. You know if you're getting it right because you stop having maintenance challenges, or your rate of maintenance challenges disappear, your rate of failures drop, your rate of incorrectly applying maintenance starts to drop. Those are real world outcomes. And really, it's the real world outcome that you need to loop back into the model and the data to ensure that you're constantly improving it. Last thing I'm going to say, I know I'm going on a bit here, but David talked earlier about you no longer in a world of set and forget. That's absolutely true. Systems which are dynamic, which are learning from real world data, cannot be set and forget. Otherwise, they become uncalibrated, essentially useless very quickly, or potentially become useless very quickly. And when you've got billions of dollars of infrastructure and hundreds of millions of dollars worth of maintenance schedules being informed by those, you absolutely need to keep the model learning, keep the model training, but learning against that real world outcome, that preventing failures or preventing false positives, preventing false negatives. That's the real world outcome you need to train the model back on.
Look, that's really good. What you're saying there is quite a revolution, then, really, in terms of the way you actually predict your for example, your maintenance requirements, etc. But people are going to say, and I know this I think this is on an operational level. Oh, we haven't done it that way. We've always done it this way. And I know that organisations now, there's a huge cultural or organisational barriers, if you like, in adopting physics-informed AI into operations. David, I know you've been involved in this. How does KartaSoft then help organisations navigate through this? She'll be right. We've done it. We've always done it this way. We can't be better. How do we move them into the 21st century and beyond?
I think it's an executive level conversation. It's not a maintenance conversation, right? When it comes to using our technology to actually predict failure. It's really around using it to replace assets. There's a lot of capital costs. For those capital costs, there's a lot of money that has to be had, whether they have to go out and borrow it or generate it somewhere. But with all of that, the costs associated, right, are extreme. If you are able to actually predict where your failures are going to be and where they're going to occur, you can actually then go and address the components that need to be addressed, and the components that that don't need to be addressed as quickly you can sweat your assets. It's like looking at a railway line, right? You have 1,000 kilometers of railway line. You have it going over hills, round bends, etc. And different rail wears differently in different spaces, right? And there's a whole lot of different contributors to that. So the idea around that is using physics-informed AI is to predict where the failures are, where the rail, from not just from a wear perspective, but how it's going to wear over a period of time, right? And in what areas. And it's identifying all of those areas of where the failure modes are going to occur. And that's it goes back to, in the asset space, it's reliability-centered maintenance as opposed to scheduled reactive maintenance. Scheduled reactive maintenance, we work blind. An asset reaches a certain piece of asset reaches a certain age, whether it's rail or pipeline, and we'll rip that out and put a new piece in because it's got to that age. Where with reliability-centered maintenance, now you're looking at you're using the data to inform your decisions, right? And you're using a physics-informed AI model to contribute to help with determining where the failures are going to occur. So instead of spending $700 million on maintenance, you can maybe spend $200 million. Or instead of spending 12 billion, you can spend 3 billion, right? The numbers are high, especially with with massive linear assets. And it's about being able to identify the performance and with real world contributors to the performance of the assets as to which assets would need to be maintained and which wouldn't.
So you've got to validate these predictions. I mean, what you're saying sounds extraordinarily powerful, but KartaSoft can come in and say, we can do all this, but how does KartaSoft validate this initially? What sort of testing or blind testing, or what do you do to actually show the business, not just say it, but actually prove this, that this is actually going to work? David, any thoughts around that? I know that must be a problem that occurs all the time.
So where our approach is very, very scientific and very rigorous. Our approach is we'll take 3 to 4 years of data. In some cases, there may only be 10 failures in that period, but that may be sufficient for us to generate our predictions. So we'll take 3 to 4 years of data, and we'll use that for our machine learning. We'll take a year of data that's used for training, that's separated, that we use for our testing, and then the client keeps the last year of their data, right? And once we've built our model and we've optimized our model for their environment, we then take that data and test it against our model and produce ROC reports, ROC curves, which actually show the performance. It shows the performance of our model. It shows how well we can predict, and it shows the accuracy of our predictions.
So that's done right at the very beginning. There's this almost blind testing against existing data,
yes,
with KartaSoft data to see, and then let the business see those advantages firsthand. Anything, Ian, to add to that?
It's I mean, that's really the right way to do it. Predicting rare events is really, really difficult. And
It is.
the idea of physics-informed AI, it's not a new one. It's been applied to jet engines for a long time. So there's a whole lot of maintenance schedules associated with engines. It's associated with large mining trucks and when to replace the tires on the trucks. And those are relatively simple environments. The complexity we're talking about here of many, 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 many kilometers of pipelines, of many kilometers of complex networks, makes this problem much more difficult, but definitely demonstrably doable. And the point about, can we show you where could we have predicted this particular rare event for you, is a really, that's what's this is the big breakthrough with this particular application, the ability to predict those extremely rare events in extremely complex systems. And the cost of getting it wrong is extraordinary. So if you have a failure in your system, the cost is measured in very, very large numbers of dollars, which is why people take this relatively straightforward reactive maintenance approach. But that's also really expensive. The ability to find these rare events, these black swans, that's the secret. That's the specialness of this approach.
Gentlemen, we've covered a lot of ground. We've moved certainly a lot further than I expected when we were starting to talk about gold standard results. And by the sound of things, it's not the product of a gold standard data necessarily. I've got some closing reflections and summaries, but anything final that you'd like to add, David Cleminson first? Anything finalised from your end?
I think that one of the key things is gold standard data is very rare. You can't afford to wait for it. There's organizations that are spending tens and hundreds of millions of dollars trying to generate gold standard data. The opportunity is it builds more resilient models that can consume that data and give you outcomes with transparency.
And Ian, any last words from you?
Yeah, for a large organization, you can't wait for perfect. Never let perfect get in the way of good. I am, of course, in favor of improving data quality over time and also use of international standards to improve data quality over time. I couldn't possibly involve in a conversation without referring to the use of international standards. But it's that's the slow burn, and that's the constant improvement cycle. And that will actually improve the quality and accuracy of physics-informed AI. So it's not a bad thing. It is worth striving for, but you can't wait. You can't wait for tomorrow to deal with today's problems.
Fantastic. Well, look, in summary, my key takeaways from today, first one, the gold standard data is rare and don't wait for it. Secondly, the models must be able to extract useful signals from noisy data. Format agnostic ingestion, brings speed and flexibility. Obviously, that's common sense. Those data lakes, those hidden costs can often outweigh their benefits. We talked about trust being built through transparency, not necessarily just perfect data, and that continuous learning obviously helps keep predictions up to date. And integration ensures that predictions drive actual business outcomes. Gentlemen, thank you for your time and interest, and it was really greatly appreciated. And for our audience, we look forward to hearing from you. Simply go to KartaSoft.com, click on Contact Us, and please forward your comments, thoughts, and questions. This is Dave Golding from KartaSoft, and thank you for your time.